Hi everybody. Today I'm going to talk to you about the first of our possible methods for vector addition or subtraction, and that's called the parallelogram method. It's not the method that I prefer, it's the method that your textbook talks about, and it kind of assumes that you're doing a very good job of drawing your vectors, both with an accurate length and with an accurate angle, which is why I don't prefer it if it's just, we're talking about my preference here, because I can kind of eyeball vectors and then I can use my calculator if I use the other method, the component method, which is the topic of the next video, video 18. But this is a great method for getting a general sense for where the vector is, so that's what we're going to use. So first off, it's the parallelogram method. So to know that, you obviously have to understand what the parallelogram is. So since it doesn't come up very often, here's the quick definition for it. I've drawn one out here. And what you know about it, 4 things. That the length, that's what these absolute value or absolute magnitude bars mean. The length of segment A is equal to the length of segment B. The length of segment C is equal to the length of segment D. And then also that line segment A is parallel to line segment B, and line segment C is parallel to line segment D. And so you can see that we have the same thing here as we have here, and the same thing here as we have here, and it describes a discrete shape there. So how can we use that to add vectors together? Well, let's imagine for a moment that I have a position vector here, x sub 1, and then later on the position changes by this much, x sub 2. And so we have these 2 different position vectors. My question for you is, where does the object end up if it changes its position by x sub 1 and then later on changes it by x sub 2? To do this, you can't just find the length of x sub 1 and the length of x sub 2 and add them together. You could find those lengths using the Pythagorean theorem if you wanted to, but that's not exactly how I would do it. And it's going to get you the wrong answer, because this length and that length can't just be added together directly. You're going to see why in just a minute. So what I'll do then is I will try to create this a parallelogram out of these 2 sides here. So you can see I've kind of got an A side and a D side right here, and so I have to add in the opposite sides. So if you think about it like copying and pasting on the computer, I'm going to copy this x sub 1 and paste it over here on the head of this x sub 2 vector. So I'm going to do my best to try to draw that out here. So here we go. Right there. It's not the best, but it'll do. In fact, I think I might just try to do a little bit better job of it. Kind of hesitated, and when you draw on this, you just kind of got to go with it. That's better. There we go. So now I have to do the same, copy and paste for x sub 2, only I'm going to start up here. So what you're going to see is it looks like this, like so. And so it should end right here at this point, right there. Okay, what's the resultant vector? How far did it actually move if it had those 2 changes in position? And the answer is that it moved that vector right there. That vector would be our total displacement, delta x, and it is called, technically, the resultant. The resultant is a name that we give to a vector sum. So when we add 2 vectors together, we get a resultant. Doesn't matter what kind of vectors we're adding together, 2 velocities, 2 accelerations, or 2 displacements, or later on 2 forces. The answer is always called a resultant. And so the resultant is right here. Now, if you're just going to draw it out for your answer, that would be great. But technically, you're going to find that later on we're going to need to give you, or you're going to need to give us, a distance or a size of that vector and also an angle. And so we're going to need to measure that angle right there, which we give the variable theta, and then you're going to have to try to figure out the size of delta x, the magnitude of it. And so you're going to see that you're going to have to somehow come up with a way of figuring out the length of that. And you might remember that in algebra, we can find the length of a line segment, or in this case a vector, by taking its x and y coordinates of its final position and subtracting the x and y coordinates from the initial position, and then squaring each of those, and then taking the square root. That's called the Pythagorean theorem, right? So for us, we started at 0, that makes sense. and then it goes over 5, right? And then up 4. And so we could figure out what the final magnitude would be. So the magnitude of delta x would be the square root of this horizontal 5 squared plus the vertical change 4 squared. And so we can figure out what that would be. Delta x, the size of delta x, would end up being, let's see, 25. I'm going to have to do my calculation here. So 25 plus 16, and then take the square root. Gives me 6.04. Excuse me, 6.40. And of course it's a displacement, so it's going to be in meters. Then it gets a little trickier. I have to be able to figure out the angle right there. And so the angle is actually equal to the inverse tangent of the opposite side, this side right here, over the adjacent side, this side right there. And so I end up with the inverse tangent of 4 over 5. And so that angle gets me, let's see, 4 over 5 is 0.8. So 0.8 inverse tangent, and make sure you're in degrees, of course, as always, gives me 38 degrees. And of course, I'm basing it off of the east axis here. So this is east, and this is north. And so you'd probably be able to say that this is 38 degrees north off of the east axis. So north of east, right there. And so that would be our answer for this vector addition problem. Okay, now vector subtraction is done the same way. So that was x, this is all for x1 plus x2 gives us this as an answer. So on a test, you'd have to report out both of those things. If I wanted to, though, I could go back and subtract the two vectors. So I'm going to erase these real quick. Okay, I took a moment to erase everything, and so now I have a question for you very quickly. If I have instead a situation where I need to subtract vectors, it's important to remember that subtraction is really just adding the opposite. And so what's the opposite of this x sub 2 variable? Vector. Well, the answer is if x sub 2 goes like this, originally, the opposite of x sub 2 must look like this. Same length, just in the opposite direction. That makes sense, I hope, to you. So what I need to do then is to redraw this in the negative direction, like so, like I have that. So I'm going to go ahead and erase what I've got here, so that doesn't confuse you. And I'm going to go ahead and draw it like so. And so the new x sub 2 vector, oof, that's terrible, looks like this. Let's see if I can do a better job of it here. That's better. This is the opposite of x sub 2. And so I'm going to add x sub 1 to the opposite of x sub 2. And I'm going to use the parallelogram method again. So I'm going to copy and paste each of these as I did before, just like I did. So it looks like this, and like this, like that. And then my resultant in red again looks like this, like so. And so I can use the same method to be able to, the Pythagorean theorem and the inverse tangent, to be able to figure out what that magnitude and direction is. So addition and subtraction, they're really the same thing in vector addition, so long as you remember that the opposite of the vector is just the same vector going in the opposite direction. That's it. Hope that helps. Good luck with the practice. Let me know if you have any questions, and I'll try to answer those. Thanks.